Okay, recording is just started. Sangmin is the director of Klaytn Foundation. Previously, he worked for Ground X as a CTO for 3 years or 4 years. So I worked with him for several years, and I'm very glad to work with him because he is a very professional computer scientist and software engineer, system software engineers. Before joining GroundX, he worked for Samsung Electronics, Samsung Research Center, and he got a Ph.D. from Seoul National University in computer science. And then he worked for Argonne National Laboratory as an assistant computer scientist. And so his major research topic was parallel programming models, compilers, and runtime systems. It's very rare in Korea. So he's very expert in system software engineering. And the reason why I invite Dr. Sangmin sir is that he can share many insight and experience to develop public blockchain platform, L1 platform. If we invite other founders from Ethereum or Polygon or Solana, we cannot hear from them about the detail of how to implement public blockchain. But Dr. Sangmin sir will share the detail of implementing public blockchain and how many challenges are there, so you can learn the real experience to implement public blockchain platform. So please give him a big round of applause. Okay.
Okay.
Okay, let's start.
Yeah, thank you, Jason. Thank you, Professor Han. So yeah, as introduced, I'm Sangmin. You can call me Sam as well. So today, as Professor Han mentioned, today I'm going to talk about the practical aspect and engineering perspective of building and operating a public blockchain, especially about layer 1 or the mainnet. Okay, let's get started. So let me skip my introduction, as Professor Han already introduced myself. And again, I'm currently the director at Klaytn Foundation. So I'm leading the entire Klaytn project after Jason. So today, I'll mostly talk about two topics, the problems that blockchain is solving and also layer 1 is solving, and the challenges and the experience that I and the Klaytn team has been experiencing. And so those will be about development and operation of the mainnet. And lastly, I'm briefly talk about the next in the mainnet development from the perspective of Klaytn. Okay. So problems. I think this is the Web3 the course. I think most of you guys already heard about these problems, but let me briefly re-emphasize the problems that blockchain or this Web3 is trying to solve. So the problem that we are trying to solve is how can we create a trust among some entities who are mostly untrusted entities in an algorithmic way. So in traditional way, so we have a central entity and they manage a database, and all the information is kept in that centralized database, so we can easily keep the consistency in the data, but you have to rely on the central entity about the immutability and the trust of that data. But in a blockchain approach, so each participant, we don't have a central database, but each entity or each participant has a copy of that database, and they ensure the immutability in a systematic way or in the blockchain way. So, I believe you guys are familiar with this the data structure. This is the typical the diagram about the blockchains in Bitcoin, and it has this a series of blocks, and each block has Merkle tree, and the Merkle tree has the tree of hashes. So I'm showing this because of the next page. So how we can define and how we can view blockchain from the perspective of computer science or computer scientists. So as I mentioned, the problem that blockchain is trying to solve is how we can create a trust between untrusted entities. But in the view of computer science, specifically the problem would be how can untrusted nodes in a network create an immutable chain of data blocks. So we have P2P network, and on top of this P2P network, we build blockchain. And from the computer science perspective, these blockchains are the singly linked list of blocks, and each block is a container of transactions. So this is a data structure. So if you want to build blockchain or mainnet or layer 1 or layer 2, whatever, so you have to be very familiar with data structure in computer science, and also need to know about the algorithm and implementation of data structures. But most data structures used in blockchain implementations are very primitive ones, like this singly linked list, but internally it has it uses complicated data structures like trie or the hash function, hashes, and so on, hash structure, and so on. And on top of this, the data structure, we use smart contract concept to implement the logics or some services. And again, from the perspective of computer science, those smart contracts are the scope of program language, and internally it has a virtual machine to execute those program languages. And from the perspective of architecture, this is a typical distributed system with a P2P network. And lastly, and the most important part is in blockchain is consensus algorithm. And the problem that those consensus algorithm in blockchains are solving is called the Byzantine generals problem that was defined by Lamport back in 1982. And so, so we are solving this consensus problem and also data immutability problem by using the traditional data structure and the program languages and the network architecture and so on. Okay, so if anyone has a question, then feel free to interrupt me. Okay, keep continuing. So, but on top of these, the fundamentals, the blockchain, especially blockchain technology, is trying to solve this blockchain trilemma problem. So this trilemma problem is no blockchain can have three attributes. The attributes are security, decentralization, and scalability. And they must choose 2 out of 3 of these attributes. So either they prefer decentralization and security, or they prefer the scalability or security and so on. So not any of them has all 3 attributes, but they prioritize 2 out of 3. In the case of Klaytn, we prioritize scalability and security. And what is blockchain platform? The blockchain platform is the platform that provides blockchain data structure while enabling blockchain-based application development. So these are a list of old blockchain platforms, but you guys can see that there are many blockchain platforms. They might be using different consensus algorithm, and they target different industry and so on. But again, the primary goal of these blockchain platforms is to provide an environment where the users can save their data or can write a programming using a smart contract concept and so on. Yeah. So then let's jump into the main topic of this talk, the mainnet, about mainnet development and operation. So I was trying to draw a sequence or the cycle of mainnet or the blockchain platform development, and actually this cycle is very similar to the typical software development cycle, but the mainnet development has some unique challenges. So from planning and defining requirements and so on, but the unique challenges in the blockchain development is at this. So one of them is how to keep the backward compatibility, because as you guys know, the blockchain cannot remove old data. It has to keep the entire history, so anyone can verify the previous data and the current data and so on. So even though the new versions are released and we develop new features, but they have to handle old chain data as well. So it's really challenging because we cannot throw out the old data. So we have to keep the comparability through entire chain history. And the second challenge is the code itself really has to be error-free. That means if there is an error, especially on the mainnet, then that might cause an entire halt, an entire suspension of the ecosystem. So if there is any error, then that could be a disaster. So that means when you develop, when you develop this mainnet, we have to really test a lot. So I would say when the development time is 1 month, we have to spend at least 1 month or 2 months to test the new feature or a new release. Lastly, the updating, deploying the new version or updating network is very challenging, and they have to be very asynchronous, because again, the mainnet or the blockchain platform cannot be stopped. So it has not, it must not stop. So some of nodes have to be always live, and that means we cannot update entire network or entire system in a single page. So there should be several pages, and the mainnet there should be a special process like a rolling update to update the entire network with a new version and new binary. And of course, the communication between node operators is really costly, because sometimes the syncing, making a synchronization between these operators requires a lot of the efforts and time and the communication. So if we if we think about the mainnet, the scope would be very broad and very wide, and like this. This is only a part of Ethereum ecosystem. It has from infrastructure and the centralized exchange and auditors and DeFi ecosystem and so on. But today I'm going to focus on the protocol and mainnet development operation part. So I'm not going to talk about NFTs and DeFi and so on, and I will mostly talk about the mainnet itself and protocol itself. So for those who are not familiar with the Klaytn, because the examples and challenges that I'm going to talk about today are mostly the examples of, mostly from Klaytn. So I would like to briefly introduce what Klaytn is and how we started this Klaytn project. So Klaytn is the EVM comparable public layer 1 chain. So that means, we actually 2018, we forked the co-implementation of Ethereum, which is typically called GEF, and we modified and so we implemented own features on top of this 2018 version of Ethereum, and we developed and tested a lot for about 1.5 years, and then launched the mainnet in June of 2019. And it uses Istanbul BFT consensus algorithm, and that consensus algorithm is run by the set of validators, which is called governance council in Klaytn, and we have unique account and transaction model. And since last year, we announced Klaytn 2.0, and we have been focusing on metaverse and games and so on. So the numbers, we have Klaytn provide 1 second block generation and finalization time, and on average, at max, it has 4,000 TPS for Clay transfers, and the gas fee is very low compared to Ethereum. So, okay, then I'm going to talk about some challenges in different aspects in the mainnet development and operation. But the first part is about scalability or performance. So again, the Klaytn performance 1 second block latency and the 4,000 TPS. Then how we can, improve the performance and how we can improve the scalability in general. So the topics that I'll mention are not that specific to Klaytn, but those are kind of general topics. But so how the reason that I'm showing these numbers is, anyway, we target these numbers, and we made it by solving some technical challenges. So compared to other chains that in 2019, those numbers are quite, these 1 second and 4,000 TPS were quite comparative. But nowadays, all the chains are improving, and they have been, providing, the better numbers, better performance, but every, mainnet is trying to improve the performance and a technical aspect. So when you try to understand the performance of the blockchain and mainnet, we have to, to first see the what kind of consensus algorithm is used in that blockchain. So the POW and POS. POS has a better performance, but typically the problems of POW and POS is they sometimes, in most cases, they have inconsistent block generation time, and also they might have chain fork or reorg, and in most cases they have probabilistic finality. So even though the block is generated and they have to the finalization, the finality is not 100% guaranteed in most cases. So, but to overcome these problems and to solve these problems, we could think of PBFT as an alternative, and that's the reason that Klaytn chose PBFT based consensus algorithm as a main consensus. So we wanted fast block generation time and consistent block generation time rather than inconsistent one, and we wanted instant finality, and we also emphasize the energy efficiency. So yeah, I believe the PBFT was introduced in the lecture. Is it correct, or do I have to explain this again?
We don't handle PBFT in this lecture.
Okay, then Okay, then let me briefly explain the core concept of this PBFT consensus algorithm. So PBFT here the PBFT stands for practical Byzantine fault tolerant, and that means this algorithm, this consensus tries to solve the Byzantine generous problem, and basically this consensus algorithm, this type of consensus algorithm uses messages and kind of voting mechanism to determine the correctness of the message. So if you look at this figure, and we have proposer and others are validators, and proposer basically broadcasts the message, and the message has to be verified by other validators. And we have 3 phases. It depends on the implementation of this BFT algorithm, but here we have 3 phases: prepare and commit. And the core idea is after the commit phase, if the older nodes, including proposer and validators, receive more than 2f plus 1. 2f here means a number of 14 nodes, and typically is 1/3 of all nodes. And if older node receive more than 2f plus 1 commit messages, then that means the messaging here, you could think it as a block, and the block is correct, and it was verified, and everyone can finalize the block was correct and correctly verified. But if those validators, any of them, some of them do not receive enough commit messages, then that block is not verified, and then that block cannot be finalized. So this is the core concept. So as you can see, the number of messages is high. So typically the complexity, the message complexity is order of n square. But the strengths and advantage of this consensus algorithm is immediate finality is guaranteed. So again, if the older node receive enough message, that means we can conclude that the block is correct. So, but as you guys can see, the number of messages is increased depending on the number of nodes. So, and again, the complexity is order of n square. So, so the original PBFT has some weakness: the complexity, message communication complexity, and also the severe attack and so on. Because how we can overcome those weaknesses is like this. So so the first one is it's not about overcoming the weakness, but regarding the finality, we can guarantee the strong consistency. So we chose 1 second as the block, the finalization time. And regarding scalability, because again, the complexity depends on the number of nodes. We have to reduce, or we have to, limit the number of nodes that's participate in the real consensus. So we made a mechanism that is called the committee selection. So I will explain this more in the next slide. And the third problem is the severe attack, because if we have many nodes, then the messages could be very high. Could be very increased. So it cannot actually, it cannot practically reach a consensus with a large number of nodes. In that case, we have to reduce the number of nodes, and that means the small number of nodes is very prone to the severe attack, because some nodes can be, can have different thoughts, and they can, do something wrong, in the consensus phase. So we so the way that we solve those problems is like this. So we have this council A council is a set of validators, and that validator set is a permissioned one. So instead of opening up this council to anyone, we restricted the qualification and the selection of these council members. And for each block, we instead of instead of making all the nodes to participate in the consensus space, we randomly select a set of council members, and we call this subset a committee. So only the members in the committee are participating in the actual consensus. And so with this, the permissioned council and a subset of the council, and we learn the BFT, specifically Istanbul BFT, on a chosen committee members. So this is how we, how we chose PBFT based consensus, and how we optimize the consensus to make it more practical, and that can be used in an open network environment. So this is, and then this is the architecture. So again, we can, with this consensus algorithm, we cannot increase the number of consensus nodes indefinitely. So we have to limit the number of consensus nodes. That means, again, it could be prone to the network attacks and network attacks like DDoS. So we have to protect consensus node by designing this 3-layer architecture. So we have consensus node internally, and then we have the proxy network node, proxy node network that's basically protecting the consensus node and connects the consensus node and the outside world. And in the outermost part is the endpoint node, and they basically interact with the users and the services in the public environment. So this is how we secure consensus node in an open network environment. Okay, there's one question. Yeah, BFT protocols, including PBFT, generate many messages for safety, and this cause high communication cost. Yeah, how many committees are active on mainnet nowadays, and what are main difference between PBFT and IBFT aside from committee selection? Yeah. Okay, good. Thank you. Thank you for questions about consensus. So currently we have in our test environment, we could afford 50 validators, and they could, all of them could be a committee, but we try to reduce, minimum. We try to keep the committee as big as 30 members size. So in reality, as of now, we have 31 council members. That means we have 31 validators, and we chose, I think, 22, 23? Yeah, 22. Yeah, 22 as the committee size. And yeah, main difference between, as far as I know, the main difference between PBFT and IBFTs are actually IBFT doesn't have a committee selection process. That's the committee selection was developed by our team. So the IBFT or PBFT, originally they don't have the concept of committee selection. Yeah, but the difference between PBFT IBFT is about view change, which means the view change here is about how we can handle a block is not, block is not issued to a consensus. So for example, some of the nodes, some of the validators have I mean, they lie to the others. And so if the consensus is not reached, how we can handle that situation is typically called view change or round change. And the PBFT and IBFT handle that situation and that scenario differently. And as far as I know, that how we can handle that view change is the main difference between PBFT and IBFT. And yeah, difficulty in keeping the mainnet liveness are many. Yeah, I would say, for example, because the consensus algorithm really depends on the communication. If there's a communication issue in the in network layer or in other layers, then the consensus time could take more, and it could it could cause the liveness issue. So communication latency or communication, the outage are the most difficult one. And also the system itself is not always it's not always for example, the storage of one node might be running out of their capacity. In that case, the node could die, and we have to, the system itself, the mainnet itself, has to detect whether some nodes are running or some nodes are not running. And in that cases, if the node is not operating well, that node has to be, excluded from the committee or the council, the council set. So that kind of thing has to be automated, but sometimes we have to rely on the operators. So that's those are some difficulties that we have experienced. Okay. Yeah. Good. Thank you for questions again. And move to the next one. So again, the consensus itself affects the performance a lot, but that's not everything about the performance, because again we try to have the fixed and stable the block time and also immediate finality. But 1 second, if we break down the time for block generation, and if within 1 second, then these are like the different pages are like this. So we receive transactions from the network, and with those transactions we create a block, and then we make a consensus, and then after consensus we broadcast the block, and then all the nodes in the network verify the block and confirm whether the block is correct or not. So everything, all these exclude, except the first phase, the collecting transactions from block creation to block verification should take and most 1 second, and everything should be done in 1 second. And we divide these pages into like this. So we allocated 250 milliseconds for block creation, and for consensus and block broadcast has 450 milliseconds, and lastly the verification and confirmation has 300 milliseconds allocation. So how we can guarantee this? Yeah, that was the really challenging one, and the idea was like this. So yeah, the challenge is like this. So the first phase, we have to create a block within 250 milliseconds, and how we can do that. So to solve this problem, we have to limit the execution time of single transaction, because if let's say if one transaction takes more than 15 seconds, how we can handle that? And if one block takes 1 second, then we cannot include that transaction in that block. And also the other challenge is how many transactions can be included in a block, to meet this time restriction, 250 milliseconds. So to solve these problems, we came up with this idea, because in a network, in a typical internet network, so time is not the property that we can make a consensus on. So because let's say when we execute this code, one node could take 100 microsecond, the other node could 90, and the node 3 could take 150 microsecond. So real execution time may differ on different node, so we cannot reach on the agreement about the time, the time in a network, in a distributed system. So we had to come up with the way that allow us to determine determine the approximate time when we see this programming code. So instead of relying on actual time, we define the computation code of each OP code, and those computation codes were used to determine the approximation of execution time. So that's one idea. So in this way, any computer can determine how much computation cost is required for to execute this bytecode. Okay, and the second challenge was the entire time. Even though we determined the approximation of execution time, we don't know how many transactions can be included in a block. So we used this timer mechanism. So we have 250 millisecond timer, and each transaction is executed, and within 250 milliseconds, those transactions are included in a block, and if we reach the time limit, then the last transaction is not included in the block, and then that will be retried in the next blocks. That was the idea, and it is actually safe to use this timer when we create a block, because again the verification is done by computation cost, not by the time, but by limiting to the actual execution time with by 250 milliseconds, that we could assume, we could safely assume that other nodes, the execution time in other nodes would be around 250 milliseconds. So that was the idea. And also we the time for block generation and the finalization is important, but that's not everything, because when you use a network, for example, the averages is also important, but the actual latency here means the time from when we submit a transaction to a network to the time when we receive the receipt from the network. So this entire time is defined as a latency, and also this latency is important because if we, the people, the users actually experience that latency from the network. So so this is the comparison between different mainnets. And also the other aspect is how stable the transaction latency is. So because when you send the transaction to a network, if it takes sometimes 1 second and sometimes 10 seconds, and average could be 5.5 seconds, but the standard deviation of those latency is too high, and we cannot, provide the users, good user experience with that unstable transaction latencies. That's why, we also, try to improve the stability of transaction latency. And one of the way was we used these separate network channels to transfer, to propagate blocks and transactions separately. And with this separate the network channels, the propagation time and propagation times are actually improved, but the stability is also very improved. So yeah, so these are the result of those that idea of using multi-channel on block propagation. So we have a huge improvement on the block transfer and also the latency time and so on. And okay, we talked about at the time and the latency and how fast it is, but the other aspect of performance is how many we can handle, how many we can process transactions per second. And again, this is very obvious, but the key is, the parallelization. We can use different techniques and different at different parts of the code and part of the algorithms. And I'm going to show one of the idea and one of the implementations actually we did. So, when we want to improve or optimize the code, we have to, of course, analyze the code first. So we used the profiler and we started to analyze which portion is taking, how much time, and we found that the function about the easy recover is taking a lot of time. So we try to optimize this. The idea was simple because those functions were used to verify the signatures. But if we looked through the code and then the algorithm, that we realized that those signature verifications can be done in a parallel way. So instead of doing this signature verification one by one, we could use the parallel signature verification. So this is the detail of the process, and let me just explain the core idea. So this is the part that takes a lot of time, and instead of doing sequentially, instead of executing these easy recover functions sequentially, we put these function calls together, and then we have this workflow. The core routine here is, you can think it as threads, and we have this thread pool, and this thread pool is used to parallelize these executions of easy recover calls. So we did also experiment, and when you use more cores, with CPUs to 36 CPUs, we achieved the performance improvement. Okay, those are these are the challenges and how we tackled those challenges in Klaytn. But I would say these are not that specific to Klaytn, but these are kind of general problems that every mainnet or every blockchain is trying to solve. The performance is always the important aspect in any system. So we'll keep continuing optimization of the blockchain mainnet. Okay, and then I'm going to talk about the challenges that are related to UX, user experience, and DX, developer experience. So the one problem that we tried to solve was about the private key and public key, and the mapping mechanism between these two. So the problem that we first thought about was, what if our private key is exposed. So if we, if we have a situation like the private key is exposed to someone, but in that case, the only way to handle that situation is we have to create a new wallet or new address, because private key is everything about that address or that wallet. And we have to tell the new address to my friends, and because I lost, and this result in losing every history about my wallet. So when we thought about this problem, the solution would be quite trivial. So instead of relying on the strong dependency between private key and public key, and public key here means the address. So how about we make private key changeable? So that was the idea, and that's how we implement in Klaytn. So the address is thought as a bank account, and private key is password, but in most blockchain, and this mapping between public key and address and private key is a one-to-one mapping. So if we know private key, and that means we know public key and then address. But the other way is not possible because of the cryptography. But what we did was we decoupled private key and the public key. We decoupled the public key and the address. So if we know private key, but we can know public key, but the address can be different. So we had this kind of flexible key management mechanism, and with this idea, we could also implement this role-based key mechanism. So at one address or one account has different private keys for different roles. So for example, one private key could be used to update these roles, and one private key could be used for signing transactions and so on. So this could be possible with the mechanism of decoupling the private key and the address. And the next one was because.
Can I have a question?
Yes, sure.
This concept is similar to Ethereum account abstraction recently implemented.
Yes.
Is it similar?
Yes, that's correct. So we also leave the account abstraction, as is actually the Ethereum's new proposal about account abstraction is actually more than this idea, but but in general, the goal of this our idea and account abstraction is the same. Basically, they want to give users the flexibility of managing private key and the flexible way to implement different logics.
But I think they implemented account abstraction in the layer of a smart contract.
Yes.
But this is implemented onto consensus layer. Is it right?
Right. Yeah. So this the Klaytn's account model was implemented inside the protocol level, but the Ethereum's account abstraction is proposed as the smart contract implementation. Yeah. And yes, you're right. Yeah.
Okay. Thank you.
Yeah, I'm going to talk about P delegation in the following slide. Yeah, thank you. So we recently again the Ethereum introduced last year, or they introduced the transaction types, but from the beginning Klaytn introduced the transaction types. So instead of relying on one envelope to to cover different types of transaction. We had the explicit and native transaction type to handle different types of transactions. The reason was that to improve the performance and to optimize the path of the implementation. And with this, we have a interesting feature that is natively implemented inside Klaytn is the gas fee delegation. So the problem was like this. Well, why do I need to pay fees when setting up my account? Because I just want to set up an account, but do I have to pay gas fee? And if my users don't have the native token in the network, how can they use the services in the network? So to resolve those problems, so we made a native way to delegate the gas fees to the service providers. So with fee delegation, the users don't have to pay the gas fee by themselves. Instead, the service providers, for example, game providers, they could pay gas fees on behalf of users by using these fee delegation features. So for fee delegation, we can use the special transaction type and the special private key. So this is one example of the one interesting example of the account and transaction models. Okay, and then developer experience. We had to admit that we cannot develop all the tools used by developers in the Web3 space. So we have, it's good to reuse existing tools instead of reinventing everything. So we wanted utilize existing wallets and the IDs and smart contract libraries and so on. And but even though Klaytn was started by forking the old version of Ethereum, we were implementing different features, and the code itself was diverges too much. So we had difficulty of using existing tools, and last year we decided to keep the Ethereum compatibility in Klaytn, and further we wanted to make Klaytn is equivalent to the execution semantic of Ethereum. So internally, so how we solve the problem is like this. We internally has two paths. So if Klaytn can be used as exactly Ethereum, so we have this ETH path is the namespace, and we have this Clay namespace. If you use the ETH namespace functions, then everything is working like Ethereum. But if you want to use Klaytn's own feature, you have to use Clay namespace. So in this way, because the tools or the infrastructures that are basically built for Ethereum are using this ETH namespace, they could easily used in Klaytn environment. But for the Klaytn specific features or Klaytn specific part, users have to use this Clay namespace. So in this way, we could achieve the Ethereum equivalence on Klaytn. Of course, the EVM itself was implemented like the Ethereum's the original one. And this is over that. We want to provide the better user experience. So, but having an really good open source environment is really challenging, especially a project like Klaytn, because we have a developer community, but it's really difficult to build a strong and then and growing developer community, and it's really challenging to have open source versions of different components. For example, the sidechain and SDK, wireless, and chain explorer, and so on. I mean, some tools are open source. Some tools have open source versions, but some tools don't have. So we decide to have open source versions of every tool and provide that technical stack to the developers and the service providers, so they can easily use the open source version to implement their idea by using those open source versions. So that was the idea, and we are we're trying to make these things. I mean, this open source package have more tools inside the package. Okay, how many? So do I have to finish by
maybe 10 minutes?
10 minutes? Okay, thank you. Okay, so next part about decentralization. So again, I mentioned that Klaytn started as a permission network, and some networks are still have a permission part, apart from Klaytn. So we want to make it permissionless, and we want to make it more decentralized network, and this is what we are trying to achieve these days. So instead of permission participation, we make it permissionless participation network, and there are many challenges, of course. Again, these challenges are related to our consensus mechanism, because we are using PBFT or Istanbul BFT for consensus. So making this consensus working in a permissionless network is really challenging, because we have to we cannot, at the moment, it's really difficult to accommodate all the nodes in the network. So we have to select some of them from the network as a set of validators. That was one challenge, and to do that, we have to define a criteria for validators, and we have to make a mechanism that actually validate which validators are qualified or not. And also we need to think about security and stability of the network with these anonymous validators. And so these are kind of, and also this is related to the architectural decentralization. Because in the view of, in the area of, in decentralization, we can think of two aspects. One is architectural decentralization, and the other aspect is political decentralization. But we currently focus on this architectural decentralization, and how decentralized in architecture are questioned by like this. So how many physical nodes are participating in the system, and how these computers or how these nodes can tolerate the faults or the outages in the network. So to conclude, to achieve the architectural decentralization, we have many nodes participating in the consensus, and that number should be increased. So this the idea, and this is the problem that we are solving. And again, we have 1 second finality, and two, but in a physical network, the physical latency actually affects the distribution of the nodes in the world. So if we measure the latency even within the AWS environment, we could afford about 100 or 150 milliseconds, but above that, it's really difficult to make a consensus within 1 second. So the idea to solve that problem, we might have the regional selection, and that's what we are trying to solve these days. And regarding the political decentralization, that part is affected by governance council, because we are trying to distinguish validators and governance council members, because validators are in charge of operating the physical node, and but the governance councils is basically in charge of the governance and the decision making of the network. So we are also working on how we can decentralize this governance council and that membership. Yeah, let me skip this one. And lastly, I want to talk about the network operation part, because this is very important in the mainnet development and operation, because as I mentioned in the beginning, the mainnet cannot stop. It has to always be running, and that is really challenging. And the outage or incidents is very critical to the mainnet. So we have to, have a good monitoring system and incident response process and systems and so on. So this is a typical process of the incident response. So we do monitoring, but if something happens, then that incident has to be propagated quickly, and we try to resolve that issue, and we recover from the issue, and make a bug patch and release again, and we do postmortem. So we have a strong DevOps team who is in charge of this process and this operation. But again, this is a public network. Others are also participating in the node operation, and we have to collaborate with anyone and all the node operators in the network, and that's also very challenging. So yeah, scope of network operations includes infrastructure setup and maintenance, automation and monitoring, and so on. And typically the DevOps engineers in the mainnet team is working on this part. Yeah, again, this is a diagram of long change, and this is one of the challenges that we have to deal with the BFT consensus and in our network, in many BFT based network. I'll just skip this part. And this is an example of the outage handling incident response that we actually experienced 2021. There was the most significant outage in the history of Klaytn, and it took 36 hours to recover everything from the first from the time that the incident occurred. So this is the process and what we tried through the 36 hours, and later, after we recover, we published the incident report, and we did postmortem and so on. So what we learned from that incident was like this. So incidents can occur at any time, so it is necessary to quickly recognize and respond to them, and so on. So but the third one is I'd like to emphasize, we need the regular training for incident response, because we had this big outage, significant outage in 2021. Since then, we didn't have a significant one. So for more than 1.5 years, we didn't experience any significant outage. That means people and operators might be loose in responding to this kind of accident. So we need a regular training or regular drill, yeah, to be ready for that incident. Again, this incident could happen due to the bugs or errors in the code, but it could happen due to the network situation or some other reasons. And the interesting thing was also, this is the thing, and actually it could make us implement a new mechanism for gas fee. So early last year, we experienced a lot of the arbitrage transactions, and it actually, yeah, consumed all the capacity, the full capacity of the mainnet, and we had to deal with this issue. And we analyzed a lot, and we had a lot of discussion to come up with the idea, and finally we had implemented this dynamic gas fee pricing model. So basically, the idea is, in normal cases, the gas fee is very cheap, but if there is a burst of transaction or the increase, steep increase of transactions in the network, then the base gas price is increased, and we have upper bound and lower bound, and this the dynamic gas fee adjustment is done automatically based on the network situation. So this is also, this deep from the design phase, it's really difficult to come up with this kind of idea, but while we are operating the actual network, we experience that abuse from the real uses, and then we came up with this idea to overcome that, the arbitrage transactions. And next, yeah, the things that we learned a lot from mainnet development operations are like this. So good things first. So the pioneering a new development or a career path that no one else has gone before is really meaningful. So because, yeah, nobody implemented blockchain, and nobody, this kind of the mainnet, and this is a new challenge, and solving difficult problems and developing good technology that many people can use is also very rewarding thing. And it's fun to solve various factors such as values and performance and constraints. And solving these things all together is really fun. Yeah. But there are also challenges, sometimes, again, this is the mainnet is typically a non-disruptive distributed system, and yeah, keep this system evolved and alive is really difficult. And practical difficulties to find people or developers who are interested in or suitable for this kind of mainnet development. And lastly, the mainnet development is not that visible to the public. So if everything is going smoothly and no one acknowledges that effort, but if something wrong happens, then there's a lot of critics and a lot of, newses and so on. So it's also very challenging, and it's very difficult one. So I'm not sure how many, audience are interested in the development of mainnet, but if this sounds very challenging to you, then please try the mainnet development, and especially if you are a person who digs into the problems and likes systems and enjoys helping others develop better, then you are the person who you're the person for the mainnet development. Okay, and the last part I'm gonna skip because you guys can see this from website or our Klaytn Medium. And if you have any questions, I try to answer your questions. Thank you.
Okay, thank you for your wonderful lecture. Do you have any question from the audience? Okay, in chat box.
Okay, the first question was about how we can measure the decentralization. Okay, the degree of decentralized, I would say. So we, the last year I met a research team in UK. They are working on this part. So uh, they are they are trying to make a systematic way to measure the degree of decentralization, and that degree comes from, I mean, could come from the architecture level or the governance part and any part of the network. And so and yeah, so there are some metrics that measure the decentralization. So for example, so that the research team in the UK is working on that, but the metrics that I'm aware of are Nakamoto metric and so on. And those there are some metrics that measure things, measure the degree of decentralization. Yeah. I'll try to find and share it with Professor Han later. And PIP 44H. Okay, the second question is about BIP44HD, the hierarchically derived wallet. Correct? Is it correct?
Deterministic.
I have
Hierarchical deterministic wallet.
Yeah, deterministic wallet. Yeah. Yes. So actually, the Klaytn's, I mean, if we don't use that, if we don't change the private key of the address, that you can actually use this HD wallet feature. So any following addresses can be derived by using this HD, I mean, wallet functionality. But if you change the private key, for your address, then this HD thing, it's not working. Yeah.
Okay, I will give you one more question. Maybe this will be the last question. Could you tell us why computer science students should be interested in public blockchain platform, or specifically developing blockchain platform? It looks very difficult and very challenging. So why we should be interested?
Okay, that's a good question and a very difficult question. So, if you look into the architecture or technical stack of blockchain, and it has a lot of parts of computer science. So if you like many areas of computer science, then blockchain or blockchain mainnet would be very interesting to you. But if you are more interested in the service development, but then the mainnet development might not be best fit for your interest. But if you like computer science, and if you like different areas, if you have interest in different topics, for example, operating system, programming language, and network, and performance optimization, and so on, then the blockchain is the really good fit for your interest and your career. Yeah.
Okay, thank you for the answer and thank you for your wonderful lecture. And please give him a round of applause. Thank you.
Thank you.
So,
Thank you.
okay, please stop the recording.